All right, welcome to The Explainer. Today, we're going to dive into something that's like the absolute core of all engineering, error. And look, this isn't about making mistakes. It's about understanding and, taming the uncertainties that are just everywhere. So, to get our heads wrapped around this, I've got a puzzle for you. What in the world could target practice and building a giant bridge possibly have in common? I know, it sounds kind of random, but the answer unlocks a principle every single engineer has to live by. Okay, so to figure out that puzzle, we've got to first nail down two super important words, accuracy and precision. Now, they sound almost the same, right? But in the engineering world, nope, they are worlds apart. And honestly, the best way to get it is by thinking about target practice. Okay, so imagine every measurement you take or every calculation you run is a shot at this target. In this first case, yikes, the shots are just everywhere. They're not consistent and they're nowhere near the bullseye, which, by the way, represents the true answer you're looking for. This is pretty much the worst case scenario. You're inaccurate and you're imprecise. All right, now check this one out. The shots are still pretty scattered, right? So we're still imprecise. But if you were to average them all out, find the center of that cluster, bam, it's right on the bullseye. So this is what we call accurate, but imprecise. You're kind of right on average, but any single shot could be wildly off the mark. Now this one is sneaky. It's dangerous, actually. Look how tightly grouped those shots are. That's precision. Your results are super consistent, super repeatable. The problem? You're consistently hitting the wrong spot. This is what we call bias, and it's so risky because that precision can totally fool you into thinking you've got the right answer when you absolutely don't. And here it is, the holy grail, the goal. Your shots are in a nice, tight little group, and that group is sitting right on the bullseye. This is what every engineer is striving for. It means your work is repeatable, it's consistent, and it's correct, accurate, and precise. Okay, so we want to be accurate and precise. Got it. But here's the next big idea. Not all errors are the same. Being off by 1 centimeter could be a complete non-issue, or it could be an absolute catastrophe. It all depends on the context. And that brings us to the difference between absolute and relative error. So to really see what I mean, let's picture two totally different jobs. First up, we've got to measure a tiny little rivet, let's say it's 10 centimeters long. And for our second job, we're measuring the entire length of a massive bridge, 10,000 centimeters. Okay, now for both jobs, the tiny rivet and the huge bridge, let's pretend our measurement is off by the exact same amount, 1 centimeter. That's our absolute error. The raw number is identical. So does that mean the error matters just as much in both cases? Not a chance. Think about the bridge. It's 10,000 centimeters long. Being off by 1 centimeter, that's practically nothing. When we look at the relative error, the size of the mistake compared to the size of the whole thing, it's this teeny, tiny 0.01%. For a bridge, yeah, we can probably live with that, no problem. But now let's go back to our little 10-centimeter rivet. That same 1 centimeter error is gigantic. The relative error here is a massive 10%. Can you imagine a critical part being 10% off? That could lead to a total catastrophic failure. It's a huge deal. And that right there is the key takeaway. It's why engineers are absolutely obsessed with relative error. The raw number, that absolute error, it just doesn't tell you the whole story. You have to compare it to the size of what you're measuring. All right, let's switch gears a bit. We've been talking about errors you might make with a tape measure. But what about the invisible errors? The ones lurking inside the most powerful tool an engineer has, the computer. So here is a secret about computers. They don't have infinite memory. That means a number like pi that goes on forever and ever? A computer can't actually store it perfectly. It has to chop it off somewhere. And you know what's wild? It can't even store a simple number like 1/10 perfectly in its binary system. This tiny little imperfection, this leftover bit, that's what we call round-off error. Now, you might think, okay, so it's a tiny error, who cares? Well, check this out. It's how these tiny errors can stack up. If you tell a computer to add 0.0001 to itself 10,000 times, you'd think the answer should be exactly 1.0, right? But it's not. Look at that result. Each one of those 10,000 additions had a tiny round-off error, and they all piled up, leaving you just a little bit short of the actual answer. This whole thing leads us to a really fundamental concept. a hard limit on a computer's precision. It's called the machine epsilon. Basically, it's the smallest number you can add to the number 1 and have the computer actually notice a difference. Anything smaller than that, it just gets lost in the noise, completely invisible to the machine. So we've got round-off error, which is basically the computer's fault. It's a hardware limitation. But there's a whole other kind of error, and this one, well, this one's on us. It's an error we introduce on purpose. It's called truncation error, and it happens when we decide to use a simpler, approximate formula instead of the perfectly exact but maybe super complicated real one. You know, like, instead of using calculus to find the exact slope on a curve, we might just draw a straight line between 2 points and call it a day. That gap between our simple straight line and the actual curve, that's truncation error. So let's be super clear on the difference here. Round-off error comes from the machine. It's built into the hardware. We can't really escape it. Truncation error, though, that's a choice we make. It's a trade-off. We're simplifying the math to make a problem solvable, and we're accepting a little bit of error in return. Okay, so if we've got errors from the computer and errors we're putting in ourselves, how does anything get built? I mean, how are planes safe? How do bridges stay up? It seems impossible. Well, the secret isn't about avoiding error. It's about controlling it. And one of the most powerful ways to do that is with something called iteration. So instead of trying to solve a huge, complex problem all at once, engineers will often start with a pretty rough guess. Then they'll run a calculation that makes that guess just a little bit better. And then they do it again and again and again. Each loop, each iteration, just inches them closer and closer to the real answer. But obviously, you can't just keep iterating forever. So when do you stop? How do you know you're close enough? This is where engineers set up something called a stopping criterion or a tolerance. Before they even start, they decide, okay, this is the level of error I'm willing to live with. And the computer just keeps churning away until the improvement from one step to the next is smaller than that tolerance. And at that point, boom, the answer is officially good enough. And that whole idea of good enough, that really gets to the heart, to the soul of what engineering is all about. It's not about finding the one perfect, flawless answer. It's about the art of making smart, intelligent approximations. This quote just nails it, doesn't it? The point isn't to get rid of all error, because a lot of the time you just can't. The real goal is to understand it, to measure it, and to keep it on a leash, making sure your final answer is accurate enough and precise enough to get the job done right. So that's where we'll leave it. Engineering isn't really about finding those perfect, clean answers you see in a textbook. It's about making tough, disciplined calls when things aren't certain. And this art of approximation, this whole process of deciding what good enough actually means, that's what lets us build the entire modern world around us. Which really leaves us with the big question, right? In a world that's getting more and more complex, how do we make sure we keep making those judgments well?